Hey everyone, welcome to this explainer. If you're staring down the barrel of a physics exam covering electromagnetic scattering and you're feeling a little overwhelmed by that giant wall of math in your notes, take a deep breath. You are in exactly the right place. Today we're taking a notoriously terrifying math-heavy university exam question and turning it into our literal blueprint for success. Okay, let's dive into this. We're going to break down these complex derivations step by step, decode the physical story hiding behind the formulas, and make sure you walk away totally prepared to crush this topic.
Here's our game plan for today. We'll start by tackling the exam question, then defining differential scattering, moving right along into the free electron derivation, calculating the total cross-section, comparing scattering types, and finally looking at why the sky is actually blue.
All right, Section 1, Tackling the Exam Question.
So let's look the beast right in the eye. We're facing the actual exam paper head-on today. Check out question 4. Just look at that point breakdown. Part A is 2 marks, Part B is a massive 6 marks, and Part C finishes it off with 2 more. That's 10 total marks on the line just for electromagnetic scattering. I know, it looks super intimidating, but hey, here's the good news. We've got the exact answers mapped out from the notes, and we're going to solve these exact questions and ace parts A, B, and C together right now.
Section 2, Defining Differential Scattering.
Let's lock in those first 2 marks with question 4A. It literally just asks what is meant by differential scattering cross-section. Now here is your golden ticket definition. It's the distribution of scattered average energy as a function of scattered angle per unit solid angle per unit time, all divided by incident energy per unit area per unit time. Okay, I know, that is a total mouthful, but essentially, it's really just a precise way to measure how the energy hitting a particle gets distributed and scattered across different angles in space.
To really nail this and guarantee full marks, we've got to back it up with the math. The formula is d sigma over dm omega equals w scat divided by p incident, all multiplied by r squared. So let's break those variables down real quick. W scat is the intensity of the scattered energy per unit time through a unit area. And P incident, well, that's just the incoming or incident energy per unit time through a unit area. Now here's the really cool part, and the absolutely crucial takeaway you've got to remember. Look at how the units cancel out. Because of how these intensities and that distance squared interact, the differential scattering cross-section actually boils down to the physical dimension of area. Write that down, and boom, those first 2 marks are in the bag.
Moving right along to Section 3, the free electron derivation.
Now we're shifting to the absolute heavyweight of this test. Question 4B. This is the 6-mark derivation for Thomson scattering. Listen, derivations are scary when they just look like one giant, endless wall of math. So, we're going to chunk this up into 3 logical phases. Phase 1, establishing the equation of electron motion. Phase 2, finding the dipole moment. And Phase 3, calculating the radiated energy. When you break it down like this, you aren't just memorizing algebra, you know? You're actually telling a physical story about an electron.
So let's walk through the first 2 phases of our little story. Imagine a free electron, right? It's got mass m, charge e. Suddenly, wham! It gets hit by a plain polarized monochromatic electromagnetic wave. What happens? Well, the wave forces the electron to move, and this gives us our equation of motion, which is really just force equals mass times acceleration. So m times the second derivative of x with respect to t equals the electric force of the wave. Now, because this poor electron is being shoved back and forth by the wave, it's oscillating. And in physics, an oscillating charge behaves exactly like a dipole. That leads us straight to our next crucial equation where we establish the dipole moment P. The wave hits, the electron shakes, and suddenly it's a radiating dipole.
Now this setup brilliantly illustrates exactly how that radiation spreads out. Once the electron is doing its dipole thing, we have to figure out where all that energy is actually going. We've got our free electron sitting right at the origin, our scattering angle theta, our polarizing angle phi, and alpha, which relates to the electric vector of that incoming wave. To figure out the differential cross-section we talked about earlier, we've got to relate these 3 angles. Using just a little bit of geometry here, the derivation reveals that the cosine of alpha equals the sine of theta times the cosine of phi. I cannot stress this enough. Squaring this specific relationship is the absolute key to unlocking the rest of this 6-mark answer.
All right, Section 4, Calculating Total Cross-Section.
Okay, guiding you into the final phase of this derivation, we just take those angles and plug them right back into our differential scattering formula. And beautifully, it simplifies down to r0 squared times sine squared alpha. But here is the massive shortcut, the critical trick for the exam. If the primary wave is unpolarized, meaning randomly polarized, we actually have to average the angles over phi. When we do that math shortcut, the average of sine squared alpha just becomes 1/2 times 1 plus cosine squared theta. We plug that in, and there it is. We've arrived at the famous Thomson scattering formula for differential cross-section. D sigma over d omega equals 1/2 times 1 plus cosine squared theta, all multiplied by r naught squared. From here, finding the total scattering cross-section, that just requires us to integrate this formula over all solid angles.
And when you run that integral, you get this incredibly clean result. The total scattering cross-section, sigma t, equals exactly 8 pi over 3 times r naught squared. Take a second to celebrate because you just locked in those 6 massive marks. As a quick bonus fact for your notes, since r naught is the classical radius of the electron, this specific value evaluates out to 0.665 times 10 to the negative 28 square meters. And notice again, just like we said earlier, the final dimension is in fact area.
Section 5. Comparing scattering types.
Honestly, fantastic job getting through that heavy math. Let's cool down a bit by tackling the final 2 marks in question 4C. This one just asks us to distinguish between Thomson, Rayleigh, and resonance scattering. Think of this matrix as your ultimate cheat sheet. Let's break it down really quick. First up, the type of electron. Thomson scattering, the one we literally just derived, deals with a free electron. Rayleigh and resonance scattering, they both deal with bound electrons. Next, look at the frequency dependence. This is absolutely vital. Thomson scattering is totally independent of the frequency of the incident radiation, omega. Rayleigh scattering, however, depends heavily on both the incident frequency and the natural frequency of the bound electron. Basically, it happens when the incident frequency is much, much smaller than the natural frequency. And finally, resonance scattering kicks in when the incident frequency exactly matches the natural frequency of the bound electron. If you can sketch this table out on your exam paper, you are 100% guaranteeing those final 2 marks.
And check out how perfectly this graph maps out the table visually. It plots the total scattering cross-section as a function of frequency, omega. You see that flat line extending out to the right? That's Thomson scattering. It's totally flat because, like we just established, it is completely independent of frequency. Now look at that curve gently rising up from the origin. That's Rayleigh scattering, which scales up really rapidly as the frequency increases. And finally, you can't miss it, that massive sharp spike right in the middle? That's resonance scattering, happening right at the exact moment the incident frequency matches the natural frequency omega naught. Seriously, this one single graph tells the entire story of question 4C.
Finally, Section 6, Why the Sky is Blue.
So, we've totally crushed the exam question. But before we wrap up, I really want to anchor all this abstract math into the real world. I mean, you might be sitting there wondering, what on earth does a bound electron scattering an EM wave have to do with my daily life? Well, just look up. Sunlight is an electromagnetic wave, and the air molecules all throughout our atmosphere are packed with bound electrons. Because the frequency of visible light is way smaller than the natural frequency of these air molecules, their interaction is perfectly governed by Rayleigh scattering. Remember the formula from our cheat sheet? It showed that scattering is highly dependent on frequency. Mathematically, that translates to being inversely proportional to the wavelength to the 4th power. Simply put, shorter wavelengths get scattered incredibly strongly. And since blue light has a very short visible wavelength compared to, say, red light, when sunlight hits the atmosphere, that blue light is scattered violently in absolutely all directions. So when our eyes look up and see this heavily scattered light, that exact mathematical relationship, 1 over lambda to the 4th, is the literal reason the daytime sky appears blue.
So the crazy thing is that the exact same math sitting on your exam paper is the math that paints the sky above you every single day. Which leaves me with one final question for you to ponder. If Rayleigh scattering makes the sky blue by scattering all those shorter blue wavelengths out of the direct path of sunlight during the day, what does that tell us about the physics of a stunning deep red sunset when the sun drops low on the horizon? Think about how much more atmosphere that light has to travel through to reach you, and what wavelengths are actually left over to hit your eyes. I really hope this explainer helped lower your cognitive load today and made this exam blueprint feel way more manageable. Best of luck on your test. You've absolutely got this. And hey, keep looking up.